Hello everyone, this is Shomik. Welcome to our YouTube channel GATE ASPIRANTS. In this channel, we will discuss about the subjects that are included in GATE, especially for instrumentation engineering. You will be able to receive details about the subjects and you will be able to develop the problem solving skills from the typical problems that will be discussed in the following episodes. For my part, I am going to start with analog electronics, digital electronics and microprocessors, measurements and optical instrumentation. Now I am going to start with analog electronics. So the syllabus of analog electronics include diode circuits, BJT biasing and amplifiers, FET biasing and amplifiers, op-amp, active filters, feedback amplifiers and oscillators. Now we're going to start our journey with diode circuits. So what is a diode? Diode is a two-terminal device with nonlinear current voltage characteristics. The two terminals are the positive terminal or the P terminal and the negative terminal, the N terminal. The P terminal is called the anode and the N terminal is called the cathode. Now this diode has two operating modes, the forward bias and second the reverse bias. In forward bias, the P terminal is connected to the positive and in the N terminal is connected with the negative. So the application of the positive and the negative voltage across the diodes is actually what biasing is. This is forward biasing. Now if we reverse it, say that we give the negative voltage at the P terminal and the positive voltage at the N terminal, this becomes the reverse biasing. Now we take the help of a circuit to understand the current voltage characteristics of a diode properly. This is R resistance and the voltage drop across it is VR, and this is ID or the current through the diode, and the voltage drop across the diode is taken as VD, and we take the voltage supplied by the source is E. Now we apply KVL in this circuit. So after applying KVL in the circuit, what we get is E minus VD, that is the voltage drop across this diode, minus VR, that is the voltage drop across this resistance VR, and this sums up to 0. Therefore E is equals to VD plus VR, that is E is equals to voltage drop across the diode and the voltage drop across the resistance VR. Now we are going to draw the load line characteristics of this diode. This is VD and this is ID. Now say for example we take this point as E and this is ID, that is the current through this diode. So this ID can be also expressed as E by R, that is the resistance over here, that is the voltage by resistance is the current that passes through this circuit. Now if we join this line, this becomes the load line. And now, according to the diode characteristics, we get a nonlinear curve like this. So this is the characteristics of the device. Now, this point is called the Q point or the quotient point. Quiscent, quotient point. Now if we draw a line parallel to the y-axis, this point is VDQ, and if we draw a line from here parallel to the x-axis, this point is IDQ. Now the theoretical relationship between the voltage VD and ID, that is the current flowing through the diode, is given as this: ID equals to I of S into exponential to the power VD by nu VT minus 1. Now this minus 1 is not raised to the power, it is exponential minus 1, and this is the power of this exponential term. It is often mistaken by many, so that's for that reason I have mentioned this particularly. Here we have three unknown terms, that is Is, nu and Vt. Now what is Is? Is is the saturation current. This saturation current is the magnitude of reverse saturation current. Now nu, what is nu? It is the emission coefficient. Its value is 1 by default. Now Vt, it is the thermal voltage. It is expressed as kT by Q. Its value is 25 millivolt at 300 Kelvin. Now from this graph, if we want to express the value of Is, we have to take the reverse characteristics too. In the reverse characteristics, you will be able to find that the curve is like this, and Is is this thickness. This magnitude is the reverse saturation current, and the current portion is this. And now if we come to the topic of voltage, the point from where the graph rose, right at this point, this is V, this is cut-in voltage. Its value is 0.45 volt for silicon device. Now this was all about the PN junction diode. Now we'll talk about Zener diode. Now Zener diode, this is almost like the PN junction diode which we done earlier. Now in the Zener diode, you'll find the difference, that it is symbolic difference is this one. It's a type of summation which is not present in this PN junction diode. Now let's come to this Zener diode. Now this Zener diode is also having the same two types of biasing: forward biasing and reverse biasing. In forward biasing, the same thing, we have it over here like this, P and N, where we put positive and negative voltage respectively to this P and N, and then again for the reverse bias, we put positive to the N terminal and negative potential to this P terminal, so it becomes reverse bias. This is reverse biasing, and this is forward biasing. Now, what is the thing? In PN junction, generally we give forward biasing to this device, but if we give the reverse biasing to this diode, in practically these diodes may burn out. But in case of Zener diode, practically we put this diode in reverse biasing order, and we'll discuss how it works. Zener diode mainly works in the reverse bias, and for that we need to draw the characteristics of Zener. This is the voltage terminal, this is current terminal. This is the characteristics of Zener, where we'll see that due to the application of the negative voltage, that's a reverse characteristics is like this. And this point, if we take this point and draw a line parallel to the x-axis, at this point, this is called IK, or the knee current. And this point is called VZ, or the Zener breakdown voltage. While applying the negative voltage across the terminals of the Zener diode, that means when it is reverse biased and we have applying the negative voltage across this P terminal and positive terminal, and at positive voltage across to this negative terminal, then we see that on application of this voltage, to some extent it will function just like the PN junction diode, which we have seen earlier. It is just like PN junction over here. But after a certain voltage, due to the Zener breakdown, the current rises abruptly in the negative direction, and the voltage remains fixed. So for this reason, Zener diode is used, which was not possible in case of this PN junction diode. In PN junction diode, on the application of the reverse bias, when the current increases, current to some extent becomes fixed on application of whatever reverse voltage we give, and the result the PN junction diode burns out. But that problem was removed when Zener diode was built. So this is all for today. From the next episode, we'll be discussing about the problems that can gate related to this diode circuits and all. For the time being, keep practicing.